So now that we have an idea of how quantum computers work, what they're made of, and what sort of the premise is for this kind of new way of processing, I'm going to give you a couple of examples of an algorithm or a process that works in quantum computing that doesn't work in classical computing. Things you can only do in quantum computing because of the way that it works. So before we do that, though, a summary of how you actually do work with quantum computers. You're gonna start all your qubits in some kind of a known state. Usually that's up 0. You're going to use quantum gates to manipulate the state to do something interesting, and then you're going to measure the output of these qubits repeatedly in order to ascertain the probability distribution of the outputs. If you do it right, if you manipulate the qubits with quantum gates in the right way, then you should get a high probability for one of your possible outputs and low probabilities for everything else, and that will give you your answer. We can use this to do much more computation than we could with the equivalent number of classical bits. So a classical bit, it can be a 1 or a 0, which means that if you have n bits, you can have 2 to the n possibilities. So imagine you have 3 bits, you have 8 possibilities. But an n-bit quantum computer, each qubit could be in one of any number of different states, one of different number of different superpositions. And so what you actually end up with is an 8-dimensional vector space. Somewhere in that is your answer. And so you have a much larger space of possible answers and much larger space of possible things that you can do. So let's look at an example. Grover's algorithm is the one that we'll start with, and then we'll do another video on Shor's algorithm. Grover's algorithm is a way that you can find an answer to a question if all you have is a way to validate that answer. So in the example that Grover gives, this is a database lookup. Maybe you have an array of 8 numbers, and you want to find the entry in that array that has your answer. Maybe they're all 0, and one of them is 1, and you want to find which index has that 1. Well, in classical computing, you'd have to look through that array one bit at a time to figure out which index has the value you're looking for. That's the measure. That's the validation of that answer, right? If you know that the answer is in 5, then you can look it up in 5 and say, yes, that's correct. But you don't know how to find that yet, and this is what the Grover's algorithm does. This is, again, it requires a function that is easy to validate, but difficult to find. And so what Grover's algorithm does is going to use the fact that it's easy to evaluate the solution to actually represent that solution in the vector space. We need some way to do that. We need some way to identify or tag the appropriate solution. And Grover's algorithm uses what he calls an oracle. So this is a small quantum function that will tag or somehow modify the quantum state of a value or representation that is equivalent to the solution, right? The one where it says, yes, this is correct. We can't actually measure what's correct because that would be measuring the quantum state. That would collapse the wave function. But what we can do is modify that wave function just a little bit. And then we can do that over and over again, and those modifications accumulate, and then we get the answer. So this is a simple example of what an oracle might look like. Here we have 2 inverter gates with this Z between them. This is a poly Z gate that reverses the phase. Doesn't change the value, but it reverses the phase of that value. And so in the first one over to the left, you've got a black dot, a white dot, a black dot. This is a 1, a 0, and a 1 in terms of the input values or the quantum state values that would cause the inversion to actually happen. And so you would have 1, 0, 1 that would invert, you would get a value, you would flip the phase of that value, and then you'd undo that, right? The whole point of this is you have to undo this process. And so you'd sort of identify the answer you're looking for, you'd flip the value, and then you'd unidentify it again, right? And in this case, the value would be 5. If the quantum inputs are 1, 0, 1, that's 5 in binary. And so if 5 is the number you're looking for, then the quantum state that represents that number will be ever so slightly increased. So this allows us to search a 2 to the n solution space to find the answer we're looking for by using the oracle that knows what the answer might look like, right? It can't find the answer, but it can tell you if the answer is correct. And so we apply this oracle over and over again in order to get the answer. Now, to do this, we have to start with a uniform distribution of states, right? We can't start with them all being zeros and ones because then we won't have anything to modify. We don't have anything to manipulate. So we want to start with a uniform distribution so that the oracle can sort of tweak the answer that is going to be satisfying of the correct answer. We do this with a gate called a Hadamard gate. The Hadamard gate will take an input quantum state and will rotate it in such a way that it is a 50-50 chance that when you measure it, it's an output of 1. And you can do this starting with a 0 or a 1 or whatever. You're basically rotating the state so that it is in superposition in an equal proportion of zeros and ones. So you do a Hadamard gate, and then you get a 50-50 superposition. Now, you don't measure it right away because you know you want that 50-50 superposition. So you do this with all of the input variables, all the input qubits, and then you run the oracle, and then you measure again at the end, and you get the one of the bits that is slightly bigger than the other. So I've got a little diagram here of how that oracle works. I'll do this in a separate video because it's a little bit complicated, but it's essentially the idea is to amplify the difference of the direction of the coefficient that corresponds to an answer that would satisfy the oracle. Simple as that. Depending on how big the vector space is, you might have to apply this oracle several times, and there's a bunch of math that goes on behind that. But the result is that you can speed up a process that would normally be order n, right? Looking through the array one bit at a time is order n. Instead, you can do this in order square root of n, because as it turns out with the math, that's how many times you would have to apply this oracle to get a confident answer that this is a value that satisfies the oracle. And so this is one really simple way that you can use quantum computing to do a thing that you can't do in classical computing.